Hi everyone. So in this project, we are working with a biotech company and collaborating with McCann Health for a test kit for the diagnosis of a medical condition. The product is still under development. So in this presentation, instead, we're going to talk about the data-driven study we are working on, which is based on probabilistic programming. So in healthcare, people deal with diagnosis and prognosis of medical conditions, and traditional machine learning methods can help, but might be lacking in certain features. So instead of, for instance, you might be monitoring biological materials in a patient's blood and could be interested in the next peak. That will possibly trigger an episode. So you can predict the time until the next episode, but it would be more useful to have a time interval where the episode might actually happen. Also, with traditional machine learning, you may struggle with combining different data sources, such as family history, scan results, X-ray scan results, or test results. Also, you might be unable to incorporate expert knowledge directly, since most machine learning methods are black box models with learning algorithms. So alternatively, you can have a model where the relationship with data is defined through expert knowledge, and that also makes your model more easily explainable. So instead of traditional machine learning, you can use Bayesian methods and start by drawing a Bayesian network. Bayesian networks can be used to represent probabilistic real-world phenomena. For instance, you can model the diagnosis of lung cancer using patient habits such as smoking, and also maybe using family history. You can express different dependencies in the network by edges between different nodes, and this provides an easy and intuitive way of explaining your model. When it comes to incorporating prior knowledge, you can maybe assign probabilities for being a smoker in the population of interest, and also use your expert knowledge or previous studies to assign lung cancer probabilities given the person is a smoker. You can model different probabilities like X-ray results being positive while the person has lung cancer. You can also model unreliability in the data, such as getting a positive X-ray result while the person has no disease at all. So the goal with Bayesian learning is that given the model and the observations you want to work out the probabilities related to the hidden nodes in your network. For instance, given the data of smoking habits and family history, and also the X-ray results, you are interested in the diagnosis of bronchitis and lung cancer. And with the training data you have, you want to compute different parameters for the nodes of interest and their distributions.
So, one advantage of Bayesian methods is uncertainty quantification. So let's say you're using age to predict height. With traditional machine learning, you'd put in a single input, let's say 8 years old, and your model would give you a prediction, 130 centimeters. In Bayesian machine learning, your model gives back multiple numbers, a distribution, the mean of which is the prediction. This gives you some extra information. In this hypothetical example, Bayesian modeling shows that the heights of 8-year-olds are unevenly distributed. So now let's look at a real-world use case of Bayesian networks. So a doctor makes a diagnosis based on a questionnaire and a test. Intuitively, if the questionnaire suggests a negative diagnosis and the test is also negative, then the true diagnosis should be negative. Bayesian modeling quantifies that into, for example, a small 10% chance of a positive test. Now, if the questionnaire is positive and the test is positive, then the probability that the true diagnosis is positive is high. So for example, it might be a 90% chance. Finally, if the questionnaire and the test contradict each other, and is the slides next slide? If the questionnaire and the test contradict each other, then you aren't sure whether the true diagnosis is positive or negative. Bayesian modeling reflects that, for example, giving a probability of positive diagnosis of 55%. So it quantifies how confident you should be, given how much you trust the test versus how much you trust the questionnaire. In conclusion, Bayesian modeling can provide uncertainty quantification, work with multiple sources of data, and incorporate expert knowledge. So now I'd like to thank my teammates. Gökhan's an industrial engineer and operations research scientist. Edwin has a degree in electrical and computer engineering. I have a degree in neurobiology. And in addition, I'd also like to thank McCann Health, pischool, and Sebastian for work on this project. Thank you for your attention.